So this last section of chapter 16 is on standing wave, if I can move the thing down. And standing wave is a neat phenomenon that you're going to see about waves. It's also known as resonance because you're going to see why a particular wavelength or frequency of wave will resonate in a particular length of string. For example, a particular guitar string, a particular viola string, and we're basically dealing with waves on strings still. But all of this stuff was going to be applicable no matter what type of waves we're talking about. But this is kind of a little neat little demo that's from the PHET simulation. So I'll post the link to this on Canvas. That way, if you guys want to play around with it, you can also do that. So this is basically kind of like a wave on a string simulator. On the left-hand side, we're going to get rid of the wrench. But on the right-hand side here, this is a string that's held in place on the right. It's not going to be able to move on the right. But the left-hand side, what I'm going to do is going to change it to a pulse. Okay. And this is a cool demo because we can increase the amplitude like this, or you can send a pulse over. All right. Let's see. I'm going to reduce the dampening a little bit. Okay. You send a pulse over. Remember? And this is the idea of when a wave hits a fixed point, right? The reflected wave comes back down the other way, but inverted, right? So that's kind of a cool idea where, well, when the wave gets reflected, right, it gets inverted. We can even go to the loose end, right? Where when a wave hits a loose side on the open end on the other side, it does not get reflected, but when it hits the fixed side, it does get reflected, right? So does that make sense? Okay. This is a pretty good simulation. But what we want to actually see in this case, okay, I'm actually not going to send pulses. I'm going to send oscillations, okay, at a particular frequency, okay, and it's going to wiggle this thing. I'm going to decrease the dampening. The dampening just kind of slows down the wave, okay? And this is just a wave you can actually kind of see the wave traveling to the right, right? It has some speed to it, right? So what I'm going to do is let's say, I'm going to set the frequency to 0.8 hertz instead. Okay, and see if we see something special about this particular frequency. I'm going to increase the dampening to get rid of the wiggling at first. You guys see anything special about this wave? Anything different from the previous one where it's like a wave that's moving to the right? I'm sorry? The wavelength is longer, great, okay? But do you see a wave that's moving to the left or right? Yeah, stay in place. And these are known as standing waves, okay? And this happened at a particular frequency of the wave. And the reason I know that frequency is because I spent half an hour playing around with this thing this morning, okay? Okay, and let's see if we can get the pattern here, okay? What I'm gonna do is gonna turn on the dampening just to get rid of the energy in the wave. I'm gonna increase the frequency to 1.2 hertz. Let's get that number right, okay? And I'm gonna turn down the dampening so the wave will also oscillate once again, okay? So now, it does some weird behavior sometimes, but now, right, we have, once again, this wave just going up and down here, and this one going up and down here, right? Oh, and then the loose end is going to mess me up. I should have put the fixed end on the other side. Okay. Okay. So maybe this picture is actually a lot better. Okay. So you can see that where the green dots are, right? It's kind of staying still, but then the other part of the wave is huge, right? It's oscillating up and down. Okay. Okay. All right. I'm going to go back to 0.8 frequency, 0.8 hertz to see if we can see the pattern again. Okay. I'm going to use a lot of dampening to get rid of the initial wave and then turn it off. Okay. So besides the wave kind of standing still as opposed to moving forward, is there anything like number-wise we can say about it? besides how long the wavelength is. The amplitude is getting bigger and bigger, right? Can you tell like how many up and downs are there? 2, okay? That's 2, okay? I'm gonna go back to 1.2 hertz, and then we can see if we can count how many of these up and down loops there are, okay? Can you guys count how many up and downs there are now? 3, okay? I'm gonna turn on the, I'm gonna go to 1.6. Oops. Let's see if we can count that. Now, how many loops you got? 1, you got 2, you got 3, you got 4. Okay, so somehow I'm able to just pick the frequency and determine how many of these up and down loops there are, right? Okay. Okay. And these are basically the standing part of the waves, okay? Because you can see that they're not moving left or right. They're just kind of going up and down crazy, right? Okay. And okay, it pauses a little bit here, but then yeah, it goes back up again. Okay. So do you guys see what pattern I'm using to change the frequency? Every time I change frequency, I change it by how much? 0.4, okay? Let's see what happens at 0.4 hertz, okay? I'm gonna go all the way down to 0.4 hertz, okay? So 1.6 has 4 loops, 4 lobes. They're actually called lobes, okay? Like kind of like earlobes, okay? 1.6 has 4 lobes, 1.2 had 3 lobes, 0.8 had 2 lobes. How many lobes do you guys think 0.4 will have? We'll have 1, right? Yeah, it's kind of cool. You can actually predict all of this. If I can click in the number right. Okay. Okay. 1 lobe, right? It's just this one big swing up and down, right? Anyone ever still play jump rope when they're kids, right? That's basically what you're doing, right? Okay. So if I want 5 lobes, what should be the frequency I should set? Anyone want to venture a guess? I'm sorry? 2. Yeah, let's see if that happens. Okay, I'm going to use the dampening to take out the wave initially and set it to 2. Okay. Okay. Let's see if it happens. Let's count the lobes. You got 1 here, 1 here, 1 here, 1 here, 1 here. I forgot to count though. Is that 5? Okay. So it's kind of interesting. We can actually exactly predict this, and that's because you guys actually already learned how to do this from the previous section. These standing waves is due to interference of wave / superposition of the wave, okay? The 2 waves were actually superimposing on top of each other. It's one wave. Let me go back to the little drawing here, right? One wave that is, oh, I can't draw on this, really? Okay, all right, I'm gonna draw on the side here, okay? It's one wave, right? You have a fixed point here, and then you have the oscillation going up and down here. One wave that is going forward, okay, from left to right. So this wave is the some amplitude sine of kx minus omega t. Remember, the minus sign indicate that it's actually a wave moving in the positive x direction, okay? And then that's y1. And y2 is the reflected wave off that fixed point. Initially, it's actually upside down, but it's moving in the opposite direction, okay? So y2, right, has some amplitude also. It has the same wavelength, therefore it has the same wave number. But since it's a wave moving to the left, the sign between kx and omega t is positive, okay? Right? When you superimpose these 2 waves together, you add them together like this, okay? Right? Right, this is the left going, so this is the right going wave. This is the left going wave, right? And once again, we're gonna do our little trigonometry identity again. Okay, the one we're gonna use this time is that sine of alpha plus beta, okay? Or sine of alpha minus beta. So this will be applicable for this term. The plus will be applicable for this term here, okay? It's equal to some products of sines of cosines and sines, okay? I'll let you guys work through the long algebra of it. But where if alpha is equal to kx and beta is equal to omega t, this actually expands into 4 terms, okay? 4 terms. You get 4 different terms out of it, right? Because this one blows up into 2 different terms. This one blows up to 2 different terms. So now you have 4. It's like, why in the hell would you do this? Okay. That's because, notice here, cosine of kx times sine of omega t, you get one factor of with a negative sign here. You get one factor with a positive sign there, right? So these actually exactly subtract each other to 0. The sine term, if I can pick a good color here, right? They are actually exactly the same, so you just get double that term, right? So the resultant wave of these 2 waves going back and forth against each other, okay, is going to have twice the amplitude times sine of kx, okay, times cosine of omega t, right? You're just basically doubling this, okay? In this way, now the position dependence, okay? Remember, x is the position, right? How it depends on position. It's only a sine function. The part that depends on time is only a cosine function, okay? You're no longer mixing the 2 trig functions together, okay? What this pattern will be, if you plot this wave as a function of position, okay? There's going to be lobes that are created by the sine function, okay? And there's going to be oscillation up and down of these lobes due to the cosine function, okay? So, but, okay, this creates a bunch of 0 points, meaning here, 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 right? Where the wave is not moving that much, right? You can see on the simulation there was these points on the red dots there where the waves were not moving, well, the string was not moving up and down a lot, okay? These points can be found where we find that, well, because this depends on the sine function, right? This is basically the big sine function, right? We can find these points by figuring out where sine of kx is equal to 0, right? Where sine of kx equal to 0, that's where these points exist, right? Well, sine of kx is equal to 0 whenever k times x is either some factor of pi, right? Either 0, pi, 2 pi, 3 pi, 4 pi, 6 pi, right? Now you're making everyone hungry, right? Around lunchtime, right? So any multiples of pi, sine is actually 0, right? Okay, and therefore you can actually find, okay, the wavelength of waves that actually fits, that fits into this little diagram, because remember that k, this k factor here, is actually 2 times pi divided by lambda, right? So that's all I'm replacing here, okay? So in order to find where x is equal to 0, in order to find where, at what position x the wave is actually equal to 0, meaning trying to find all these red points, you can actually solve this equation for x, okay? So if you solve this equation for x, well, at x equal to 0, the wave's going to be 0, but that's obvious because that's the starting point. But any point where it is wavelength divided by 2, or wavelength itself 3 times the wavelength divided by 2, right? Or the general formula is that it's some integer. So this is where this sometimes trip people up. Where n is some integer, it's just a counting variable, okay? Those of you in computer science might know this very well, right? This is the counter in your for loop, right? Okay, n equals to 1, 2, 3, 4, you just count up these numbers. So if n is equal to 0, right, you get this term, this factor. If n is equal to 1, you get this one, right? Because if n is equal to 1, this is 1 over 2, which is exactly this. If n is equal to 2, right, 2 divided by 2 is 1, so that you get this factor here. If n is equal to 3, right, you get 3/2 lambda, okay? So this is just a general way to write all these terms, okay? Okay. That allows you to find these things called nodes, okay? Okay, just a name. It's just, And when you think notes, it's kind of hard to remember for me. I just because it kind of looks like zeros to me. Okay, like there's a bunch of O's, a bunch of S. That's what it looks like to me. Okay. Okay. The way I remember that nodes are corresponding to the 0 point is because it kind of looks like 0 to me. Okay. You can also find these things called the antinodes. Okay. The way I remember it is that, well, it's not the zeros, eh? Not the zeros. Okay. Okay. Because, right, you can also find where the sine function is exactly equal to 1, right, or -1, right? That's where these points are. You can actually find where the wave has its maximum amplitude, okay, where the peaks of these lobes are, okay? Because if sine of kx is equal to either plus or minus 1, then that's where the lobes are located, right? Well, sine of kx is equal to plus or minus 1 when kx is actually equal to 90 degrees. What's the next one? 270 degrees, right? Or in other words, pi over 2, 3 pi over 2, 5 pi over 2. Doing the same thing here, replacing the wave number with wavelengths. You can also calculate the positions of all the antinodes, okay? As opposed to, so this is the equation you want to kind of copy down. It's going to be on the exam, of course, if this problem was given to you, okay? So the nodes are located at n divided by 2 times the wavelength, okay? The antinodes are located at n divided by 4 times the wavelength. But here's the tricky part, okay? Be careful, okay? You count only the odd numbers, 1, 3, 5, 7, 9, 11, okay? Because the even numbers will actually give you the nodes, okay? Yeah. Right? Any questions about this? Where it's interesting that certain wavelengths fits into, or actually depending on the wavelengths of the wave you're sending it, the x positions of the nodes and antinodes changes, okay? All right. This creates some interesting situations. So let's say those of you who plays the guitar, right? When you pluck a guitar string, okay, you have one possible way for the guitar string to vibrate, which is the one where n is equal to 0. Wow, sorry, n is equal to 1, actually, sorry, yeah, okay. And you have another way for the guitar string to vibrate where you have 2 lobes. You can have a case where there's 3 lobes, 4 lobes, and 5 lobes, right? So these are actually different sound that the string can actually create, okay? And so for n equals to, oops, do that. For n equals to 1, right? This whole wave, well, but basically half a wavelength fits onto the string itself. And therefore, in this case, right, if we have a string that has a length L, okay, this guitar string has some length, so because, you know, usually on a guitar, you have some fixed length, right? That means the wavelength that will fit onto that string is actually 1/2 the wavelength. Why 1/2? Why not a full wavelength? Let's remember why. Okay, because y resultant is actually some amplitude, well, twice the amplitude times sine of, I'm going to write 2 pi over lambda times x cosine of omega t. Okay. Right? Because if you look at this lobe here, right, this is the top half of the sine function. There's actually a bottom half of the sine function we didn't draw, right? That doesn't fit onto the string. So the wavelength, I can go over here, is actually twice as long, okay? So the wavelength that will fit on a string of length L, let's say that that string is 1 meter long. The first fundamental, well, it's known as the fundamental note of that wavelength is actually twice that length, okay? So it's 2 meters, okay? That's the first wavelength that will fit into that guitar string, okay? The second note, okay, or n equals to 2 is exactly 1 wavelength, okay, or 2 over 2, okay? The third one that has the 3 lobes, okay, is 1.5. No, sorry. The one that has 3 lobes is 2/3 the length of the guitar string, okay? And then just kind of keep going like that, where the one that has 4 lobes, it'll be basically 4/2 times the length of the guitar string, okay? So you can actually calculate exactly what wavelength of vibration can exist on your guitar, on your particular string, on a if they're tied on both ends, okay? And these are the equation that that is highlighted in the book in these orange boxes, right? So you know that they're important. Where if you want to figure out what wavelengths of vibration fits onto your particular string, if both ends are fixed, right? It's just 2 divided by n, where n is some integer, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Times the length of that particular string. Okay. And that's how I was actually in the simulation was able to figure out, okay, some multiples of these wavelengths actually will be the one that will create these lobes for us, okay? Right? So wavelengths is nice, but we want to do, if we want to convert this to frequency, remember that for all waves, no matter what type of waves we're talking about, the speed of the wave is always going to be the wavelength times the frequency. So if you know the wavelength, right? If you know the wavelength and you know the speed, you can always determine the frequency, right? So the frequency is actually going to be the wave speed divided by the wavelength, okay? And therefore, if you divide the plug in this number over here, right, you will get the other equation, which allows you to calculate the frequency of the waves that will fit into your particular string, okay? And this is sort of more inverted, okay? Where n, once again, is some integer, 1, 2, 3, 4, 5, right? And then the speed of the wave divided by twice the length of the string, okay? Okay. So when n is equal to 1, oops, I can't write. When n is equal to 1, right? That means f sub 1, that's going to be equal to 1 times the speed of the wave divided by twice the length. Okay, the speed of the wave divided by twice the length. This is known as the fundamental frequency. Okay. All the other ones, if you go to n equals 2, n equals to 3, 4, and 5, those are known as overtones. Anyone or music majors or know how to play an instrument that knows these terms? No one today? No overtones? Yeah. Some of the previous classes had that, okay? So that's the application for, if you have a guitar, a viola, violin, bass. Sorry, I keep forgetting what the instrument is. Cello, yeah, the big one. Yeah. Because it doesn't match with the other ones. It sounds completely different from violins and viola. Okay. So that's how those particular instrument makes a particular wavelengths of sound. Therefore, a particular frequency. That's why they have a particular sound to it every time you basically pluck the string of it. Okay. Not only is it also not just useful in music, but whenever you use a laser, right? Lasers actually used these days for a lot of things, for communication, for making cat run around, stuff like that. Lasers are actually also using these things called the standing wave, because the way that you amplify the laser light is by basically containing that electromagnetic wave inside these cavity. Remember when I show you guys the oscillation, right? It got bigger and bigger and bigger and bigger, right? And that's because in a laser, okay, the thing you're making bigger and bigger is actually the electromagnetic field, which turns into light. So it makes a very bright light because you're able to amplify that light by putting it into basically making it a standing wave as opposed to a traveling wave, okay? That's one application. We don't have to know this, but this is just something that's, people invented in, 60 years ago. and to figure out how to actually amplify light. And it changes a lot of stuff around us. Okay, so let's do an example. Okay, this more physical example, more wave on a string example. So let's say we have a string that is fixed at both ends. So I'm actually going to start drawing this. Okay, so we have some string that's fixed at both ends. Okay, it has some mass of 0.0090 kilogram. It's nice that they give it to us in SI units at least. Has some length of 3.00 meter. Okay, and the string is under some tension of 200.0 newtons. Okay, and the question asks you, well, the string is driven by some variable frequency, so it's actually able to, someone's basically just plucking the string. Okay, find the wavelengths and the frequencies of the first 4 modes. Okay, this word modes, okay, tells you what n number is. Okay, meaning when they ask you for the first 4 modes, they want n equals to 1, n equals to 2, 3, and 4. Okay, that means they want n equals to 1, 2, 3, and 4. Okay, that's the first 4. Okay, if they want the first 5, you go up to 5. You want the first 8, you go up to 8. Okay, so those are this n is known as the mode number. Right, to find the wavelengths that fits into this, right, the first one that will fit is actually this one, right, the biggest one, the longest one. Okay, and we know that you go up here, right, the wavelength that will fit in here is just 2n divided by L. Okay, so we know what L is. So lambda, let's say do 1. So in this case, n is equal to 1. Okay, and then the wavelength L, sorry, the length of the string is 3 meters. Okay, and then we divide that by 2. So 1 over 3.00 divided by 2. Did I do that right? Yeah, I did that wrong. This should be twice the wavelength. Yeah, I did that wrong. Couldn't copy down a formula correctly, right? All right, let's copy down the formula first. Okay, it was 2L divided by n, right? That's the formula. Okay, and then when n is equal to 1 is 2, right? L is 3 meters, n is equal to 1. Therefore, the first wavelength, the longest wavelength that will fit on the string is actually 6 meters. So lambda 2, right? We're just changing 1, this number is the n, right? 1 to 2. So that's actually equal to 3 meters. Okay. Lambda is 3, so it's 2/3 times 3.00 meter, right? That's actually equal to 2 meters. Lambda is 4, that's actually 2/4 times 0.300. This is basically 1/2, so that's 1/2, 1.5 meters. Okay. You guys see how I was able to calculate all the different the first 4 wavelengths that will fit onto the string. Okay, and if they want 10 of them, you just have to list them all, right? You just keep plugging it into the same formula and then just keep getting them all. Okay, all right, wavelengths is the easier part usually. Okay, the frequency, right? If we want to calculate the frequency, what we want to do is we basically want to take, well, let me just copy down that formula, otherwise I'll make the same mistake again. Okay, is n times v divided by 2L. Okay, double check that. Yeah. Okay. Right. In order to calculate the frequency, we need to know the speed of the wave on a string, right? How do we calculate the wave of the speed of the wave on a string? Any idea? Right. Exactly. Okay. We're given the tension. We're given the mass and the length, so we can actually calculate the mass density. Okay. The mass density is actually 0.009 kilograms divided by 3 meters, right? Because that's the total mass of the string. This is the length of the string, right? Okay. We calculate that. I have that in my sheet. Calculator. Okay. So this tension is 200. Oh, I need to calculate what mu is first, didn't I? divided by 3, inverted, times 200, all square rooted. I got 258. Let's do 4 sig figs just to carry more sig figs around, meters per second. Okay. So if I want to get the fundamental frequency, or n equals to 1, right, it's just the speed divided by twice the length. Okay. Divide that by the length of the string is 3 meters divided by 6. Okay. That's going to be 43.0 hertz. Okay. Right. You can plug into this formula for 2, 3, and 4. Another way to calculate this is that the cool thing about these frequency is that there's another way to calculate it. Okay. All the other frequencies is actually related to the first one. Okay. Where f sub n is actually n times the fundamental frequency. Okay. Remember when I did the oscillation simulation, right? I took 0.4, then I took 0.8, 1.2, 1.6, 2.0, right? These are all just multiples of the fundamental frequency on that string. So since this is the fundamental frequency, right? If I want f sub 2, I just take 2 times 43 hertz, and I get 86 hertz. F sub 3 is going to be 3 times that, right? Wherever that number happens to be, actually 129 hertz. F sub 4 is 4 times the fundamental. Okay, another word, 172 hertz. Okay, right. So that's how you calculate these different wavelengths and different frequencies. Okay. All right. Any questions? Ethan, do you mind passing out the course evaluation? So, any questions before I have to leave the room while he's passing that out? There's no worksheet today because we're doing the evaluation instead. We're going to see this again when we deal with sound, so I'm not too worried about not having a worksheet on it. Okay.